Alright, this is chapter 16, and we're ready for actual, the true section 3. And so we're actually going to get into talking about the periodic table. Okay, so the history of the periodic table, how the periodic table came about, is that originally we had all these elements and we didn't know what to do with them. And so there was a Russian chemist. He was actually a teacher. His name was Dmitry Mendeleev. And he was trying to figure out a way to teach his students about these elements. And so he was like, you know what? I need a way to teach my students. So he came up with a table. He started to arrange the elements in a way that he could actually teach his students. And so that's how he came up with the first periodic table. And so he arranged all of the elements in that time by increasing atomic masses. So the first periodic table was made by increasing atomic masses. And so his chart found that there were chemical properties found in lighter elements that could repeat in heavier elements. So he started to know that there were patterns. And so that's where the term periodic comes from, is that periodic just means repeating in patterns. And so he called it the periodic table. So when he started making his periodic table, he started to leave blanks for things that were not lining up properly. So things that, like chemical properties that just weren't quite, lining up with other elements. And so he was able to start predicting new elements that we didn't know about at that time, that had not been discovered, based on how things were lining up. So, and that's still used today. That's why we have some elements that they've given, like I said, the whole UUV thing. Those are elements that we are at some point probably going to make or discover or find. We just don't have them yet. So, but we know that there's going to be a place for them based on the chemical properties of other elements that we have. So, by his periodic table, here's just some predictions that he made. So he predicted this element, he called it at the time ecosilicon, okay, which turned out to actually be germanium. He predicted its existence in 1871. We actually found it in 1886. Its mass he predicted was 72. Here's what we concluded it to be. He said it had a high melting point, which it really does, 9,000 degrees Celsius. Here's what he predicted its density to be. Look what it is. He said it's going to be a dark gray metal. It's a gray metal, and what its density is, and there you go. So, I mean, come on. I don't know how else to tell you. I mean, pretty cool what he could predict just based on his periodic table. Now, next up though is a man named G.J. Moseley. So Henry Moseley. He was a young English scientist in 1913. Basically, he found that with Mendeleev's periodic table, there was a few errors. An example of that would be cobalt and nickel, that if you arrange them by their masses, they don't fit in just exactly correctly. So he was the one that he found the atomic numbers for the elements, and he said, let's arrange the periodic table by the atomic numbers. So, and that's how the current periodic table is used today, by those atomic numbers. So the current periodic table was basically put together by Henry G.J. Moseley, and it's arranged by atomic numbers. So, the periodic table, the atoms are sorted by properties. The vertical columns, vertical, remember, means up and down. Those are called groups. Sometimes they're also called families. And these each have similar properties. The horizontal columns, horizontal means left to right. Those are called periods. There are 7 periods on the periodic table. You're going to notice when we talk about the periodic table, there's lots of things with 7s. And the horizontal increased by 1 proton and 1 electron. Here's a periodic table. It's just kind of showing you what a period looks like and what a group or a family looks like, just so you can see. We're going to go through and we'll talk about these groups a little later in class, so here's just to kind of give you, so if you need this as a reference. Okay, our electron cloud structure. The electrons have different amounts of energy. Scientists model the energy differences of electrons by placing electrons in different energy levels. Energy levels close to the nucleus have lower energy levels than farther away. So what this is talking about is that you have some atom, we'll call it atom X, okay, that it has different energy levels. Electrons close to the nucleus, so we'll call that little X there the nucleus, have really high energy, versus if we have an electron that's way out here, they have lower energy. Here's kind of the key right here. Elements in the same group have the same number of electrons in their outermost energy level. Okay, and so the outer energy level, it's kind of key here, the outer energy level determines the chemical properties of the element. So whatever's in this outermost energy level, how many electrons, determines what kind of reactions that actual element will go through. Now, the next periodic table shows you, now the periodic table is split into what we call the group A and the group B elements. I've outlined at the top what the group A elements are. The group A elements, as you see, that's how many electrons are in there, what we call the outermost energy level, or I'll refer to as the outermost shell. So you'll see that this column right here, those are the 1A's, so they have 1 in their outermost shell. 2A's, they have 2 in their outermost shell, meaning that if we drew the nucleus of a 1A, okay, you have 1 electron in its outermost shell. 2A's would have 2 electrons in their outermost shell. 3A's would have 3 electrons in their outermost shell. Okay? And so you can tell just by its placement how many electrons it has in its outermost shell. And that's going to lead us to, that tells us how it acts, how it bonds, and we are going to talk about some other diagrams. We're going to talk about Lewis structures a little bit in a separate class time period. And that's what this is talking about, electron dot structures. We'll draw a little bit more of these later in class. It was founded by a guy named G.N. Lewis, an American chemist. And it uses the symbol to represent, and we'll do some examples together in class. It'll be a little easier. I'll put together a separate video just in case you missed class to go through that. Okay, group 8A. These guys, these are your, what we call the noble gases. These guys have a complete outer shell, meaning that they are completely full. For the most part, they are completely not reactive, meaning that they do not like to react with anything. They have their outer shell filled. They're happy. I like to use that a lot, that they're happy. That's the goal of everything, to get 8. So why would they need to get any more? So the only exception to the 8 rule is helium. Helium has 2, and it's happy with 2. Okay, and we'll probably talk about that a little bit more when we talk about the Lewis structures if we haven't already. Okay, now we have metals, nonmetals, and metalloids, and again, we're going to do some coloring in class. You'll have a periodic table that looks like this, that breaks down, you know, what's the metals, what's the nonmetals, and the metalloids. Again, I want to put this in the video, though, just in case you need this, so you can see the distinct elements that exist as, you know, metals and nonmetals and all that good kind of stuff. So you have that. So it's distinct for future reference. Metals are in that diagram before. They're the pinks. Most are solids at room temperature. You've got mercury that is not a solid at room temperature. So that's pretty much the only solid that's not. Shiny, they can be drawn into wires, meaning that you can pull them out and make them into wires. They can be pounded into sheets. They're good conductors of heat and electricity. That's the properties of metals. Then you've got nonmetals. If you go back a little bit, you can see the blue boxes on that periodic table. Mostly they're gases. They're brittle. They're poor conductors of heat and electricity. Basically, the complete opposite properties of metals are your nonmetals. Then you've got that category that's what we call in the middle. And those are your yellow boxes in that periodic table. You'll see they lie right on a stair step. Call it the stair step. If you go back to that periodic table, you see that there's a line on the periodic table. They're called semimetals. Semimetals, they have the properties of both metals and nonmetals. Now, something else about the periodic table. There are 7 elements that actually do not exist in the world by themselves. Meaning that if you ever come in contact with these elements, meaning that if they are in their pure elemental form, they're going to exist as pairs. I call them twins sometimes. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine all exist as pairs, meaning that pure hydrogen exists as H2, like this. You probably have seen this one, O2. Okay, they exist in what's called a diatomic form. There has to be 2 of them. You'll never see just O out in the environment. It has to be O2. And this comes in a real important play when we start writing reactions, that you understand that these particular elements always exist as 2s. They're never in their pure elemental form. You'll never find just pure oxygen by itself. You might see an O by itself if it's in a compound, like H2O. That's illegal. You can find an O, see how it's with another element. That's okay. But if you're just finding pure O by itself, it has to be a 2. Now, this again is where I'm talking about the 7, how it comes into play. The diatomic molecules, sometimes I refer to them as the magic 7, because there are 7 of them. They make a number 7 on the periodic table. Look at this over here. They make a 7. And if you're looking at a periodic table, they start at number 7. They start at nitrogen. Oh, I kind of checked the wrong thing. That's okay. The only exception to that is hydrogen over here. That's kind of a, weirdo that sits over here by himself. So if you can, for the most part, just remember that you start at nitrogen, which is number 7, and make a 7. Just don't go all the way down here to acetine. Okay? And then add hydrogen in. Then you can remember what your diatomics are. There's always new elements being made, created. In 1994, they found a new one, number 111. In 1996, found 112. They're at the time that they made your book, they were working on 114 and 116. I know they found 120. I mean, there's always new elements being formed, being made, however you want to put it. So, we're always adding to the periodic table, making it bigger, expanding it, all that good kind of stuff. So, all right, the end.